5 and 6 get combined together. And that's going to go with that packet that I just handed out. So make sure you've got the right packet. Make sure you didn't accidentally give you the wrong one. It should be 6, 5, and 6. And then we'll do Chapter 7, Section 3 on Thursday. So make sure you have this packet here. And we're going to look now at work questions. Now, what we do for these is we set them up as a fraction. And they're actually very, very easy to do. There's only a few of them in your homework, but it's something, again, that you'll see in college algebra. So we're going to look at question 59. Now, what we do is we set them up as a fraction. So a chef can finish a catering job in 6 hours. A student can do the same job in 12 hours. How long will it take them to do the job if they work together? Well, if they work together, we know that it's going to take less than 6 hours, right? Because the professional chef can do it in 6 hours by himself. If he has a helper, that's going to make it less. So what we look at is how much work is done per hour. So we look at how much is done per hour. So the professional chef, it takes him 6 hours to do a catering event. So how much is done in 1 hour? Well, if it takes him 6 hours to complete the job, then in 1 hour, he's done 1/6 of it. Make it a fraction. So if it takes him 6 hours to do the job, he does 1/6 in 1 hour. Now, what about the student? Well, the student, it takes him 12 hours, or her 12 hours to do the catering job. So how much does the student do in 1 hour? 1/12. And we're going to let x equal the time. Now we put our equation together, and we use our fractions here. So we've got our chef. So the chef, in 1 hour, he does 1/6. So we're going to take 1/6, and we're going to multiply it by our x there. What about the student? Well, the student is 1/12. And we multiply that again by x, because we look at how much is done per hour. Now, this is always going to equal 1, because that's 100% or 1 catering job. So all of these equations equal 1. Now we just simply clear it. Pretty easy to do. We'll clear our fractions. So we'll multiply everything by a 12. So multiplying through, 12 divided by 6, that's a 2x. 12's cancel, that leaves you with an x. 12 times 1, that's a 12. That gives me then 3x equals 12. Divide by our 3. And now we've got it as 12 divided by 3, which is 4. And so it should take both of them working together 4 hours to complete the job. That's all you have to do, is write them as a fraction, clear the fractions, and solve. And that makes sense, because what do we know about the professional chef? By himself, he takes 6 hours to complete the job. If he has a helper, what should that do? That should make it less time, right? And we know that 4 hours is what? Less than 6. So all we do for these is write them as a fraction. Question 60 is very, very similar. A printer can complete a large job in 8 hours using a new machine. Using the older machine, it takes 24 hours. How long would it take them to complete the job if they use both machines. So both machines are going to work together. We set this one up exactly the same as the last one. So we've got a new machine, and that new machine takes 8 hours to complete a job. And how much is done in 1 hour? Well, in 1 hour, that's 1/8. The old machine takes 24 hours. And how much is done in 1 hour for it? 1/24. We're going to let, again, x equal the time. And what does our equation look like? Well, we put them together. Why are they going to be added together? Because they're helping each other. Now, if they were working against each other, it would be subtraction. So an example of them working against each other might be draining and filling a pool at the same time. You're putting water in, at the same time you're taking them out. That would be subtraction. In this case, though, they work together. So now what do we have? We have our new machine, and so it's 1/8x. Add that to our old machine, which is 1/24x. And what does it equal? 1. Why does it equal 1? Because that is one job, or 100%. Right? 100% is 1. So you're going to do one job working together. Now we just simply clear our fractions. So we're going to multiply all of this by 3. Or not 3, 24. It's going to clear our fractions here. So when I clear my fractions by using that 24, 24 divided by 8, well, that's a 3. 24's cancel. That simply leaves you with an x. 24 times 1, well, that is 24. Putting them together, we then get 4x equals 24. Divide by your 4. And so x now equals 24 divided by 4, which is 6 hours. So those two machines work together. It should take you about 6 hours, right? And that makes sense because the new machine can do it in 8. And if it has another machine helping it, that's going to speed up the process. And 6 is definitely less than 8. So we know we did it correctly. Let's try another one here. How about question 67? This is one that has subtraction. So 67 says a vat of acid can be filled by an inlet pipe in 10 hours, and it can be emptied by an outlet pipe in 20. How long will it take to fill the vat if both pipes are open? Well, what are we doing? We're adding more in, and we're taking out as well. So when we take it out, that's going to be subtraction. So that's going to be subtracted off. So I'm going to represent the emptying of this vat with a negative. Okay, so when we fill up this vat, when we put water in, acid in, it takes 10 hours to fill. So that means 1/10 is filled in 1 hour. When we're draining it, it takes 20 hours to drain. Now, because it's going out, I'm going to go ahead and put a negative here. That way we don't mix up the signs. So how long does it take to completely drain, or how much is done per hour? Minus 1/20. And x represents, again, the time. Now, why are these being subtracted? because you're adding acid and taking it out at the same time. So let's put these together, and we have 1/10 x minus 1/20 x, and that again always equals 1. Clear out your fractions by multiplying everything by a 20. And 20 divided by 10, that's a 2x there. 20's cancel, leaves you with a minus x. And 20 times 1, that's a 20. Putting those together, we get x equals 20 hours. Right? So it's going to take 20 hours to completely fill up this tank with acid when we're filling it and draining it at the same time. So that's all you have to remember, is either it'll be addition or it will be subtraction. And this goes along with the first 4 questions from your homework. And I made these multiple choice just to make it a little bit easier so you know if you're on the right track or not. So 1 through 4 is here. These are all of your work-related questions. So all the work-related questions are 1 through 4. So your homework, 1 through 4, are all the work-related questions. There are other questions in this section and other topics, but we just don't have enough time to cover them, and you'll see them in college algebra. A lot of times our textbook goes into more detail than what we really need, but I wanted to make sure that we at least looked at the work questions. So now we're going to move on, and we're going to look at 6.6, which is variation. So variation, we'll see again in college algebra. And variation is how certain things interact. So an example of that is, let's say, how long does it take to stop a car? Well, what do we know? We know the faster the car goes, right? The longer it takes to stop the car. That's direct variation. Faster speed, longer time to stop the car. Same thing with the weight. A heavier car takes longer to stop than a lighter weight car. And that's called direct variation. One influences the other one. Another example of variation is how long does it take to drop. Let's say I have something in my hand. Let's say I have a marble in my hand and I drop this marble. What makes it go down? Gravity. Okay? Now, it's going to fall pretty quickly on Earth, right? But if I'm on the moon that has less gravity, what happens? It takes longer. So gravity is also part of that variation. And they're just how formulas and how properties interact with each other. And there can be one thing that influences another, or there can be multiple things, or it can be inverse variation. So we're first going to look at direct variation. When we talk about direct variation, that means we multiply. We're going to be looking at direct variation first. Then we'll talk about inverse variation. And when we talk about inverse variation, that means we divide. And also joint variation. And joint variation just means we have multiple parts. So these are the 3 types that we're going to be looking at. Direct variation, if you see the word direct, multiply. Inverse, we divide. Joint variation, that just means we have multiple components going together. So going back to that car example, all right, how long does it take to stop a car? If we put everything together, we've got the weight of the car. We've got maybe the speed of the car. You might have the type of brakes the cars have. All those go together, and that would be joint variation. So one thing, direct, multiply. Inverse means we divide, and joint just means we have multiple parts. And K is going to be the constant that we have to find. And that constant is something like gravity. So gravity would be a constant. Also, pi is a constant. When you look at circles, right? 3.14 goes on forever. That's another example of a constant. So on each of these, we're going to have to set up our equation, plug in values to find the K, and then rework it with the new numbers. They're actually pretty easy to work through. They're not difficult as long as you're careful with the setup. A lot of times students struggle with the setup. Once the setup is done, it's easy. Okay, so let's look at an easy one here. We will start with question 47. Okay, so we're going to look at question 47, and this is on page 440. So page 440, we're going to look at question 47. The weight of an object on Earth is directly, see that word directly, that means we multiply, directly proportional to the weight of that same object on the moon. A 200-pound astronaut would weigh 32 pounds on the moon. Why does he only weigh 32, or she? Because gravity is less on the moon, right? We're going to have to find the new gravity. How much would a 50-pound dog weigh on the moon? Well, how do we set this up? We have the word directly. That means we're going to multiply. So it says the weight of an object on the Earth is directly proportional to the weight of the same object on the moon. So what does our formula look like? And you can label it however you would like. I like to use words. I think it's easier. So we're going to look at the weight of the object on the Earth. That's going to equal K times the weight of the object on the moon. So that's our equation. Right? It's multiplied over here. We have our constant. So that means we multiply. Now, what do we know? We've got to fill in our values, and we have to find K. So what do we know? It says a 200-pound, so we can see here, a 200-pound astronaut weighs 32 pounds on the moon. So let's plug in our values. So we know the astronaut weighs 200 pounds on Earth, 32 pounds on the moon. So we'll put 32 here. And then we have to find our K. Now, all we need to do is divide, reduce it down, and get our K. So we're going to divide it by that 32. And we'll reduce that down as much as we can. So 200, divide that by our 32. And if we reduce that down, that gives us K to be 25 over 4 or 6.25. Either one. I'll probably keep the fraction here. Now we relabel our equation, rewrite it. And the Earth is going to be that 6.25 or that 25 over 4 here times the moon. So That's what we have. That's our equation. We found our value of K. Now, we want to find out how much a 50-pound dog weighs on the moon. Right? So we know Earth is going to equal to K times the moon. We solved it out. We found our K. Now, what do we know? We know the dog weighs what? 50 pounds on the Earth. So if the dog weighs 50 pounds on Earth, what is it going to weigh on the moon? We plug our values in. So we know this dog weighs 50 pounds on the Earth. We don't know the moon weight. So that's going to be left here. You can use the variable x if you want. I don't. I like words. I think it's easier. And we want to just clear our fractions. So we'll just multiply both sides by our 4. And that's going to then leave you with 200 equals, 4's cancel, 25 times the moon weight. We'll divide by our 25. And when we do that, what's the weight of the dog on the moon? Well, if we divide out, we have that 200. Divide that by our 25. We get 8 pounds. So that dog should weigh 8 pounds on the moon. Is everyone okay with how I did that? So what do? We set up our equation. We find our K. That's the first thing that we do. Rebuild our formula. Plug in the new value that we want to find. Calculate it out and get our answer. So that dog that weighed 50 pounds on the moon, on Earth, is going to only weigh 8 pounds on the moon. Why is that? Because gravity is less on the moon. So that's why the dog weighs less. Okay, let's look here at question 49. So the volume of a can of tomatoes is directly, now see that word directly, that means we multiply, directly proportional to the height of the can. If the volume of the can is 300 cubic centimeters, when its height is 10.62 centimeters, find the volume to the nearest whole number with a can of a height of 15.92 centimeters. So what do? First thing we need to do is build our formula. Volume of the can. So that's going to go on the left. We're going to build our formula here. This is question 47. So we are looking at the volume of a can of tomatoes. And that volume, now we always have a K, so that's there. And what is it? It's directly proportional to the height. So the volume equals some number times the height. What happens if you increase the height? You increase the volume of the can, right? The more it can hold. Volume is how much it holds. Now, what do we know? We know, 49 on this one. That one's 47. So 47, this one's 49. So what do we know already? We know that the volume of a can is 300. So that goes here. Equals K, which we don't know. And the height of that can is 10.62. So the height goes in there, and the volume goes in there. Now, if we have decimals, we can just use decimals. So we're going to divide both sides by that 10.62. So if you have decimals, you can write your K as a decimal. And now we can find our K. So that's the first thing that we do. That's our constant. We have 300. Divide that by 10.62. And we'll take this out, let's say, 3 places. That should be more than enough. So that's 28.24 if we round 9. If we round 9. So there's our K. So what does our formula now look like? Well, our formula looks like the volume equals 28.249 times the height. Now, what do we want? It says find the volume, the nearest whole number, with a can height of 15.92. So we want volume with the height, right, of 15.92. So all we have to do, plug our values in. So volume equals that 28.249. Multiply that by our 15.92. And when we multiply those out together, what do we get here? We get 28.249. Multiply that by 15.92. And that gives us 449.72 if we round 4. Now, we want it to the nearest. It says here, nearest whole number. So that's going to be about 450 cubic centimeters. And that's how we set up that formula and work it out. So all you need to do is first find your formula, calculate your K, use the K with the numbers provided to come up with the new answer. That is direct variation. Now, it can also be direct variation to a power. And so we'll look at 52 next. The amount of water emptied by a pipe varies directly, so there's directly there, as the square of the diameter. So we have to watch that. So we're going to have to square. For a constant water flow rate, a pipe emptying into a canal will allow 200 gallons of water to escape in an hour. The diameter of that pipe is 6 inches. How much water would a 12-inch pipe empty into the canal in 1 hour, assuming the same water flow? So what do we know? We know that the water emptied into a pipe varies directly as the square of the diameter. So you can label this however you want. I'm going to label this as the water equals K times the diameter. But in this case, it is squared, right? Because it says varies directly as the square of the diameter of the pipe. So make sure you notice that squared there. And what do we know? We know that pipe can push through 200 gallons of water in an hour, and the diameter of that pipe is 6. So we have to square that 6 there. So that is then going to be 36K equals your 200. We'll divide by our 36, and then we can reduce that. And you can either leave K as a decimal, or you can use a fraction. It really doesn't matter. I'll just use a fraction, and that's going to be 50 over 9 there. Okay, so that's your K. You could just as easily have used the decimal. Doesn't matter. I just used the fraction. So what does our formula look like? Water equals 50 over 9 now times the diameter squared. Easy enough. What do we want? It says, how much water would a 12-inch pipe empty into the canal? So we're going to use a 12-inch pipe. And that's going to be your diameter. So what does our new formula look like? We plug it in. The water usage, or output, is going to be 50 over 9 times 12 squared. And we know 12 squared is 144. And 144 can cancel out with that 9 right there. And that's going to leave you with a 16. And 50 times that 16 comes out to be 800. And so it would move through 800 gallons of water. That one was directly to a square. So direct always means multiply. Now, what about inverse? Well, we talked about it earlier. Inverse means you divide. So the next one's going to be inverse. Let's look now at question 55. And you've got to make sure you watch out for inverse. Remember, inverse, watch the wording here, that means you divide. Okay, so 55 is going to be inverse variation. The frequency of a vibrating string varies inversely. Key word there is inverse. Inversely to its length. That is, a longer string vibrates fewer times a second than a shorter one. Now, suppose the piano string is 2 feet long and it vibrates at 250 cycles per second. What frequency would this string of 5 feet long have? Well, let's set up our formula. Frequency varies inversely as its length. So what would our formula look like? Well, our formula looks like frequency equals K. Now it is inverse, and it's inverse to the length. There's our formula. We're going to be looking at the frequency here. Should be Y. So what do we know? Well, it says piano wire is 2 feet long. Frequency is 250. So frequency is going to be the 250 here. K is the unknown again. Length of that wire is 2. Quickly and easily solve this by cross multiplying. And what does that give you K to now be? Well, when you cross multiply, K equals now 500. And K might be different with different strings. Okay, different materials on the strings, that's going to change the K. So let's rebuild our formula. So the frequency is going to be now 500 over the length. And what do we want? We want to use a length of, when we look at question 55 here, we want to change that length to 5 feet. So we'll plug our value in, calculate it, and we're done. frequency is then going to be 500. That's our constant K. We'll divide that by our 5. So that comes out to be 100 cycles per second. Okay? That's what that means. And that's going to be cycles per second or hertz. So that's going to be 100 cycles per second. Now, what happened? Well, as you increase the length of the wire, it vibrates slower, right? It's a longer wire. It takes longer to go. Think of a pendulum on a clock. A really small pendulum is going to go really fast, but a longer one is going to take longer for it to go. So, as you increase the pendulum length, or in this case, the length of the wire or the string, that makes it move slower. So fewer cycles per second. So that's inverse. Inverse variation just means you divide. That's it. Let's look at another one. How about 58? The force with which Earth attracts an object above the Earth's surface varies inversely as the square. So we have to be careful there. Inversely as the square of the distance from its center. So inversely as the square. Now, what does inverse mean? Divide, right? But it's squared, so that distance is going to be squared below. If an object is 4,000 miles from the center of the Earth, it is attracted with a force of 160 pounds. Find the attraction if the object were 6,000 miles away. The further you are away from the Earth, the less pull it has. So let's try to come up with our formula. What do we know? We know the force used to attract an object varies inversely as the square of the distance. So we'll just say the force here is going to equal K over the distance squared. So it's going to be, this is going to be squared below. Now we'll fill in the pieces. And so what do we know? Well, it says an object that is 4,000 miles from the center of the Earth is attracted with 160 pounds of force. So 160 equals K over your 4,000 squared. That's our distance squared. And we're going to square that 4,000. Yep. It comes out to be quite a bit bigger than that. When we square that, it comes out to be this, which is, there's 16 million, right? So that comes out to be 60 equals K over 1, 2, 3, 4, 5, 6 zeros. And now, how do we find our value of K? Well, we just simply cross multiply here. And what does K then come out to be? And this is going to be a really large number, and that's okay. It may even go to scientific notation. So we'll multiply that by our 160, and it does. Okay? Scientific notation looks like this. This is your power of 9. So that's 2.56, and that would be times 10 to the 9th power. Or you can write it out. Okay, either way will work. You can either write it out, or you can use scientific notation. Now, what are we going to use now? Well, it says we want to find the force of this object for attraction if it's 6,000 miles away. So we're going to use a distance of 6,000. And that should be less, right? The further you are from the Earth, the less it's going to be. So let's plug in our values. So the force is going to equal that 2.56 times 10 to the 9th power over that 6,000 quantity squared. And we'll just work that out. Now, I already have my number in my calculator here, so I'm not going to write it again. We're going to just simply divide that by the 6,000 squared, and that gives me about 71.1, we'll round here, pounds of force. So it's less, and why is it less? Well, it is less because you're further away. How gravity works is it's the attraction of an object. And everything has gravity. This table has gravity. Okay? We don't really feel the effects of the gravity of the table because it doesn't weigh a lot. The sun has massive amounts of gravity because it's a really large sun, right? It has a lot of gravity. Earth has less. Moon has less than the Earth. Why? Because it's smaller. Some planets like Saturn have a higher gravity, higher attraction value. Okay? And the further you go away from the center of it, the less pull it has. So in this case, we went further out in the atmosphere, or out in space, and that means you weigh less. Okay? So let's do a couple more of these. You're welcome. Okay. Inverse always means divide. So just remember that. The key takeaway is inverse means divide. And you can set these up however you want with the formulas. I like to use words. It's the absolute easiest way to do these. If you try to use X and Y like the textbook does, students always mix up the pieces. Question 60. This is going to be a joint variation. The collision impact of an automobile varies jointly as its mass and the square of its speed. Suppose a 2,000-pound car is traveling at 55 miles an hour and it has a collision impact of 6.1. What is the collision impact of the same car at 65 miles an hour? Well, let's put our formula together. What does joint mean? Joint means we have multiple parts going together. So what are our parts going to be? The mass of the car, square the speed. So what does our formula look like? Let's just make our formula up here. So we're going to look at the impact. And the impact is going to equal K. Remember, that's our constant. We have to multiply that by the mass of the car, the weight of the car. And then we have to multiply that by the square of the speed. There's our formula. Plug our values in, find our K, rebuild our formula, recalculate again. So a 2,000-pound car traveling at 55 miles an hour. So the 2,000 goes over here. The 55 goes over here, but it has to be squared. We'll find our K, and that gives us a collision impact of 6.1. So now we can work it out. And we've got 55 squared times that 2,000. Okay, so that gives you 60, 50, and then 4 zeros after that. And again, you can use scientific notation if you want. we need to finish this out, so we're going to have to divide. So we're going to take that 6.1, and we're going to divide it by that number. And then 4 zeros after that. Okay, and that gives you then a K value of 0.123456. And a 1. And you could use scientific notation if you want. It doesn't matter. Let me just double check to make sure we didn't make a mistake. And I think I may have too many zeros. So we need 1, 2, 3, 4, 5 zeros. Okay, so I'll write this with the 5 zeros. So 1, 2, 3, 4, 5. Yep. Okay, so 1, 2, 3, 4, 5, and a 1. So what's our formula now look like? Well, our formula looks like the impact is going to equal 0.123451 times the mass of the car times the speed squared. So what makes the biggest difference? Well, the speed is going to make a much bigger difference than the weight of the car. Why? Because the speed is what? Squared. So increase in the speed is going to increase the collision impact a lot more than the mass will. Of course, we know something like a big Lincoln Town car is going to have a much bigger impact than a smaller car. So a big car is going to make a larger impact. But what is more important on this impact than anything else is the speed. Why? Because it's squared. So when you go from that 55 up to 65, it's going to make this impact go quite a bit up. So we want the same car, so we want to use 2,000 pounds for the mass. And we want to use a speed now of 65. So we're going to see what the impact of that collision would be. So plug your values in. So that impact is 0.12345 and a 1 times, again, that 2,000 times 65 squared. And you can do this all in your calculator, all in one step. Just type it in. Okay, there's our K. We're going to multiply that by our 2,000. We're going to multiply that by 65 squared. Look what happens here. It comes out to be a factor of 8.5, and it says nearest tenth, so that would be 8.5. So the impact went from 6.1 to 8.5. So that makes a big difference in the impact of the car. Let's look at another one. 62. The weight of a trout varies jointly as its length and the square of its girth. So that's the distance around. An angler caught a trout that weighed 10.5 pounds and it measured 26 inches long with 18 inches around its body. Find the weight of the trout that is 22 inches long and it has a girth of 15 inches. Right? So girth is the way around. So when you figure out what the weight of that fish is going to be, you know, it's how fat it is and how long its body is. Those go together. Girth is a distance around. It's like your waist size. So let's see what we have here. Weight varies jointly as its length, square of its girth. So your K, joint into the length, square of the girth. There we go. Girth, again, is just like your waist size, basically. Distance around. One angler caught a trout that weighed 10.5 pounds. So we'll plug that in. Got decimals. We use decimals here for our answer. Measured 26 inches long. And it had a girth of 18 inches. We'll go ahead and multiply. You can use a calculator, use it all at once. So 18 squared times that 26. Well, that gives you 8424K. That equals your 10.5. So we'll just divide 10.5. Divide that by 8424. That gives you a K value. We'll take this out to 4 places of 0.00 if we round 1, 2. Rewriting our formula. So the weight of that trout is going to be 0.0012 times the length of the trout times the girth. Now, we caught a trout, and we want to calculate what the weight should be. So we caught a trout. That trout was 22 inches long, girth of 15. So plug our pieces in. Remember that girth should be squared there. Don't forget to do that. So plug our pieces in. And what should that trout weigh? Well, it should be 0.0012 times that 22 times that 15 squared. And now let's just multiply them all together. So 0.0012. And then multiply that by our 22. And we'll multiply that by 15 squared. And that weight should come out to be 5.94 pounds. And it says nearest tenth of a pound. So, yeah, 5.9. So that trout should weigh about 5.9 pounds. Okay. Is everyone okay with how I did that? Let's do one more, and then I'm going to work through some of your homework questions. So let's do one more of these. This one has a lot going on. We're going to look at question 66. So this question has direct, inverse, and it's joint because it also has multiple variables. This one has a lot of things happening. We're going to look at temperature. The volume of gas varies inversely as the pressure and directly as the temperature. So this would be joint variation because you have multiple pieces going together. So the pressure that's inverse, temperature is direct. So let's go ahead and write up our formula. We want the volume of this gas, so the volume we need our K, of course. Now, what does it say? It says it varies inversely as the pressure. Directly, that means multiply as the temperature. So the temperature is going to go on the top, right? Pressure goes down below. Fill it in. So, a gas occupies a volume of 1.3 liters, 300 kelvins of pressure, 300 kelvins for the temperature, and a pressure of 18 newtons. So let's find our K. So we know the volume of this is 1.3. Now, temperature is going to be in Kelvin. There are 3 scales for temperature, Fahrenheit, Celsius, and sometimes in the physics course you use Kelvin. So the K in this case means Kelvin. So volume of 1.3, 300 K, so that's 300 Kelvin, so that goes here. And we're going to divide that by a pressure of 18 newtons. It can also be in pounds. That's English units. Everywhere else uses newtons. But if you're in America, you use pounds. Now, what do we need to do? Find our K again. How are we going to do that? Simply cross multiply. So cross multiply here, and that gives you 300K equals, we've got 18 times that 1.3, and that comes out to be 23.4 there. And we'll divide. So divide both sides by that 300. And what does that give us for the K here? K comes out to be 0.078. So there's our K. Write up your new formula and find the new volume. So volume now equals 0.078 times the temperature divided by the pressure. And what are we going to do here? We're going to change the values. We want to find the volume, so we increase the temperature to 340 degrees Kelvin. So the new temp is 340, so that's going to go in there. The new pressure comes out to be 24 newtons. So that's going to go over here. So we'll fill in our values. So we want to find our volume. That equals that 0.078 times 340 over 24. And that comes out to be a new volume of, when I calculate, 1.105, and it doesn't say how far to round, so we'll just leave it as that. And that comes out to then be 1.105, and that's going to be liters. We've got a few minutes left, so I'm going to work through a couple of questions from your homework. So I'm going to work through a couple of these from your homework here. We'll just do 2 or 3 of them. I did make these multiple choice, so it's a little bit easier. Let's see. How about we look at question 7 from your homework. For a fixed amount of principal, the simple interest varies jointly with the rate and the time. So that means they're multiplied together. The only time you divide is when it says what? When it says inverse. This one does not say inverse at all. Why does it say jointly? Because there's 2 parts going together, right, to get the principal. Simple interest varies jointly with the rate and the time. So rate and time go together to give you that interest on the principal. So if the simple interest is 1050, interest rate is 3%, that's going to have to be a decimal, so we'll convert that. Time is 7 years. We want to find the interest. So let's come up with our formula here. We'll do the formula first. And this is from the homework. We're going to look here at 6.5 and 6.6. We're going to be looking at question 7. So what's our formula going to look like? Well, the interest, that's what we want. Interest on our money. We've got a K, so we don't know. And it varies jointly with the rate and the time. So let's plug in our values here. Simple interest is $10.50. So that goes here. K is again the unknown. We want 3%. 3% as a decimal is 0.03. Time is going to be 7 years. Right, so plug in our values. Make sure you put that percentage as a decimal. So now we'll go ahead and multiply. So 7 times 0.03. Well, that comes out to be 0.21K. And that equals your 1050. Divide by that 0.21. Now we've got our K value. So 1050. Divide that by 0.21. Right, make sure you watch the decimals here. That gives you a 5,000. That's our value of K. K in this case is actually the money that you started with. So you put $5,000 in, and 7 years later you got interest of $1,050 total. So let's rewrite our formula. Our interest is going to equal that 5,000 times the rate times the time. So we want to change things up a bit. We want to change the rate to be 5%. And again, 5%, that's 0.05. And we want time to be 10 years. So what's our formula look like? Well, the interest that we make is going to now be 5,000. That's our principal. That's our K value in this case. Times 0.05. Right, times 10. Multiply all that together. 5,000. Multiply that by our 5%. Multiply that by the 10 years. And we get out $2,500. And if we did it correctly, that should be one of the choices there. And so that one looks like it's going to be answer what? Answer B. Okay, so it's going to be coming out to be answer B. We'll do one more, and then that'll be it for today. So I'll pick out one more of these. Let's look at how about, we'll just pick another one here. How about question 11? Pretty simple one here. We'll look at question 11. Now, question 11 again is inverse. What does inverse mean? Divide. That's all you have to remember. Direct, multiply, inverse, divide. So, current I in an electrical conduit varies inversely as the resistance of the conduit. The current is 7 amperes when resistance is 750 ohms. What is the current when the resistance is 842 ohms? So let's write up our formula here. This will be the last one that we're going to look at. And we know the current is going to equal K. Now it is inverse, right? Varies inversely to the resistance. And what do we know? Well, we know that we have a current of 7 amperes. So that 7 goes here. Unknown K. Resistance of that wire, or conduit in this case, 785. So we're going to cross multiply here. And that gives you now K equaling, when we cross multiply, 7 times 785. And that gives you 54.95. I'll go ahead and pass out the sign-in sheet. And if you haven't picked up your old homework, great, homework is up there. So here's the sign-in sheet. So let's go ahead and finish this one out. We have our K value. Rebuild our formula. So the current equals 54.95 over the resistance. And we're going to change that resistance of the conduit. We're going to change it to 842 ohms. So we want to change that resistance to 842 ohms. So we're just going to divide that by that 842. What's our current going to be? Well, let's calculate this real quick. We divide out, we've got that 54.95. We're going to divide that by 842. And that comes out to be 6.526, or about 6.5. And that's going to be amps. So that should be answer B there. So 6.5 amps there. And what happens as I increase the resistance? Well, as you increase resistance, current goes down. And in electrical circuits, if you have something like a short circuit, you have a resistance of basically zero, basically 1 or close to zero. That's why your current gets so high, and that's why you pull a breaker. Because resistance is how much it resists the flow of electricity. Larger wires usually have more resistance. Okay. When you have something like a complete short, that makes your current go way up. All right. So that now takes care of 6.5 and 6.6. So that's going to be your homework. So your homework is now going to be 6.5 and 6.6. That's that first page. And you should be able to do them all. And I will see everyone then on Thursday. So please make sure you sign that sign-in sheet. And I will see everyone then on Thursday. And I know there are applications. I know students don't like to do applications. I made them multiple choice, so it'd be